In this video, we are going to start looking at inference for categorical data, and we're going to start with inference for a single proportion. In many ways, this is very similar what we did from chapter 5, except now instead of estimating a proportion, we're looking at categorical data and estimating a proportion for categorical data. And you'll see from the examples it's different, but the methods of doing things is the same, so it'll seem very familiar. The two things that I also want to mention about this is earlier in chapter 5, I must have had an earlier edition or a different version of the book, so the table I was using for the normal curve wasn't complete, so I used a different table from a different book. But I found the correct table, so I used the table that is in the OpenIntro Stats book for this video. So this is the overview slide, which we'll spend about 5 minutes going over before we go over each topic in detail and with examples. We start with identifying when a sample proportion is nearly normal. So before we jump in and start using the normal table, we have to verify some things, and that's the sampling distribution for p hat based on a sample size of n from a population with true proportion p is nearly normal when, one, the sample's observations are independent. So for example, the simplest way is if you're told the sample is a simple random sample. And two, we need to see at least 10 successes and 10 failures. And the formula for that, you might have the numbers, the counts. So if you have 10 successes and 10 formulas, that's great. You actually don't need the formula. But if you don't have the counts, the formula is NP greater than or equal to 10. And that's the successes, and the failures n 1 minus p is greater than or equal to 10. And this is called the success failure condition. So when these conditions are met, these two conditions are met, the sampling distribution p hat is nearly normal with mean equals p, and this formula for standard error is equal to the square root of p times 1 minus p over n. Typically, we don't know the true population proportion p, so we have to use an estimate. For confidence intervals, we use the sample proportion p hat as our estimate. For the hypothesis testing, we assume h naught is true, so we use p naught as our estimate for p. This is important for you to know because you'll be plugging it into formulas such as standard error. Again, you don't know p, so for confidence interval, you're going to use p hat. For hypothesis testing, you're going to use p naught. A confidence interval provides a range of plausible values for the parameter p and takes the form of p hat, your sample proportion, plus or minus a z-score times your standard error calculated here. So the z-score is the one associated with the confidence you want. So these are the steps. You identify your p hat and your n sample size and determine what confidence level you want. Often confidence level is denoted with an alpha. And so often you say things like a 90% confidence interval or a 95% confidence interval. If it's a 95% confidence interval, then your alpha is going to be 5%. You're going to check, you're going to verify the conditions over here that we talked about to make sure the sample proportion is nearly normal. You'll compute the standard error using p hat and you find z star. And then you construct the interval. And finally, you make a conclusion. You interpret the confidence interval in the context of the problem. And note, z star is the z-score you look up in the table. For hypothesis testing for a single proportion, first you're going to prepare. You're going to identify the parameter of interest and list the hypothesis, H null and HA, identify the significance level, and identify p hat and n, the sample size. You're going to check. You're going to verify conditions to ensure that p hat is nearly normal under H naught. And again, those conditions are the ones of independence and also the success failure condition. You're going to use the value of H naught for p, that is the p naught value, to check the success failure. So again, over here, it's this note here. For hypothesis testing, we assume H naught is true. So in these formulas that involve p, we're going to use p naught. So if the conditions hold, you're going to compute the standard error, again, using p naught, compute the z-score, and then identify the p-value, and then you're going to make a conclusion. Again, both in confidence interval and hypothesis, don't forget your conclusion. You're going to evaluate the hypothesis and provide a conclusion in the context of the problem. finally, we're going to look at choosing a sample size. Using our standard error, we'll do an example of how to get an appropriate sample size for a particular confidence level. That wraps up our overview, so we're ready to start in detail with identifying sample proportions as nearly normal. The first thing we're going to do is take another look at sampling distribution, which we did discuss in Chapter 5, but you've now done all the mechanics and hopefully have a better feel for it. So it's a good time to take another look at this. So a sampling distribution, it's not about a single study where you go out and sample 100 people or 1,000 people or 5,000 people. It's about when you have multiple studies, each study having a sample of 100 people or 1,000 people. The next thing is you probably aren't going to create your own sampling distributions. You're going to create a single sample. Sampling solutions are what people who study statistics do. Again, this is not people who use statistics to study different things in biology or political science or what have you. This is people who do the study of statistics. And they create sampling distributions so they can come up with techniques such as confidence intervals and hypothesis testing. So sampling distributions is something that people who study statistics do. And what they do, so again, it's not practical if we're trying to study a phenomena in biology. But when you're studying sampling, what you do is you study the characteristics of sampling. And you use a simulator. You use a computer simulation so we can characterize the sampling distributions by 1, the center of the distribution will be equal to the population parameter, and 2, the spread is measured by standard error. And again, here the spread now is a result of sampling error, and 3, the shape resembles a normal distribution. So let's look at this again. So people studying statistics simulate random sampling, maybe 100 samples, but they do this 1,000 times. For each 1,000 samples, they look at their 100 sample points and compute a proportion. So each simulation produces a proportion. So if you have 1,000 simulations, you have 1,000 proportions, and then you graph that as a histogram, and you get this distribution curve. And what you see is the center of the distribution will be equal to the actual population parameter. Remember, since this is a simulation, we can actually go and calculate the population parameter for the whole set. Then we see the spread, again, is measured by standard error. And again, it's not about how far the data is distributed, but the spread comes as a result of sampling error. And the shape resembles a normal distribution. Because it resembles a normal distribution, we can use all the techniques from normal curves when we sample. So these are general things that we've learned about the sampling distribution, which will then allow us to use this normal curve to talk about our samples. So for example, suppose the proportion of American adults who support the expansion of solar energy is 88%, which is our parameter of interest. So in this case, P is equal to our proportion for our population, the entire set of American adults. So if we take a poll of 1,000 American adults on this topic, so this is one sample with n equals 1,000, the estimate would probably not be perfect, but how close can we expect the sample proportion to be to the actual proportion of 88%? Well, here we have a histogram on the left. It's a result of 1,000 samples. Each sample produced an estimate of the proportion of Americans who support solar energy. So this histogram now is a histogram of our 1,000 estimates from our 1,000 samples. And from the study of sampling proportion, again, from these computer simulations, what we expect is the sampling distribution to be normal, as you can see, and the mean of the sampling distribution will equal the actual population parameter, 0.88. And again, the spread is due to sampling error, because not every sample is going to hit at exactly 0.88. So again, this is the basis of our confidence interval and our hypothesis testing. And the reason, because this is normal, we use the normal curve when we do inference and confidence intervals on a single proportion. So the next thing we're going to discuss is identifying when the sample proportion is nearly normal. I put an abbreviated version of how to check if a sample proportion is nearly normal. First, we verify independence, and second, we verify the success-failure condition, and then we have the formula for standard error. Our first example is a simple random sample of 268 payday loan borrowers were surveyed to better understand their interest around regulation and cost. 70% of the responses supported new regulations on payday lenders. Is it reasonable to model p hat, the sample proportion, equal to 0.7 using a normal distribution? First, we will check independence, and here, the easiest way to check independence is for a simple random sample, and here the experiment says it's a simple random sample, so we can say yes, this is a simple random sample. The second thing we check is our success-failure conditions. We need at least 10 successes and 10 failures. It doesn't really tell us how many successes and failures there are, but they say 70% of the 826 supported new regulations. So we can do this calculation as 826 times 70%. That's going to be, it's going to be greater than 10. Also for the failure, then 826, now 70% supported regulation, that means 1 minus 70% or 30% did not. And so when we multiply these two together, we also have a number greater than 10%. So both of these conditions are met. And just some notes, so the probability distribution of p hat is nearly normal with mean equals p. That is if we repeated the sampling process 1,000 times to get 1,000 estimates of p hat and looked at the probability distribution for the values of p hat, the distribution will approach normal and the mean of p hat will approach p. The spread, which is usually measured in standard deviation, is due to errors in the sampling process. So we measure the spread using standard errors. For proportions, we use this formula here. Continuing with this payday loan, let's say 51% said they would support regulation that would require lenders to pull credit reports and evaluate debt payments. Is it reasonable to model p hat equals 0.51 using a normal distribution for a hypothesis test here? And the answer is yes, because one, it's a random sample, we have that here, and two, because our success rate, that's n times p, which is 826 times 51% is going to be greater than 10. And our failure rate, n times 1 minus p, that's 826, 1 minus 0.51, which is 0.49, is going to be greater than 10. Continuing with that same example of 826 payday loan borrowers, 51% saying they'd support some sort of regulation, use hypothesis testing to evaluate whether the poll provides convincing evidence that the majority of payday loan borrowers support this new regulation. And by majority, we're going to say that's greater than 50%. Pulling some of our data together, so our p hat for our payday loan borrowers now was given as 51%. So this is p hat that comes from our poll. We're doing hypothesis testing, so we need an H0, a null hypothesis. In this case, that says like there's nothing interesting, kind of like it's the very most vanilla thing. And the most vanilla thing you can have is no one has an opinion, which is almost equivalent to saying 50% like it, 50% don't. It's like a wash. So H0 is going to give us P0 is equal to 0.5 or 50%. Or in other words, no one cares one way or another, which I know isn't exactly no one cares because maybe 50% feel strongly one way and 50% feel strongly the other, but we're going to say it's a wash, so no one cares. Standard error is P times 1 minus P over N all square rooted. Again, for hypothesis testing, we're going to assume H naught is true, which means P we're going to assume is 0.5. So it's going to be 0.5 times 1 minus 0.5 is also 0.5 over the number of n is the size of the sample, which is 826, so we'll get 0.017. And so the question of hypothesis testing becomes, if we assume H naught is true, that is P naught is equal to 50%, what's the probability of getting a sample with P hat equals 0.51? So we need to look at P hat, 0.51. We're going to convert this to standard units so we can look at this using the normal table. So Z of 51% is 51 minus 50 all over 0.017. And I should put a percent here because this should really be percent. And that's going to give us a Z-score of 0.59. That is 51 is 0.59 standard errors away from the mean. Yeah, so be careful because this is actually 51% minus 50%. So in decimal, this is 0.51 minus 0.5. So looking at 0.59 on your Z-score table, so here's 0.5, here's 0.500, 0.501, 0.502, all the way down to 0.5 and then 0.9 is 72%, represents the area under the curve that's less than Z-score 0.59. So I'm just going to draw that here. Z-score 0.59 gives us 70% of the error under the curve. But this 0.72 actually isn't what we're looking for. It's like not the droids you're looking for. It's actually kind of the area around your P naught. In other words, you want to know if you're centered around this value here of P naught equals 0.5, you want to know if you're within 0.59 standard errors, either bigger or smaller. So again, the area you want is the area between negative 0.59 and positive 0.59. But this is something we can figure out. So let's start with our 72% graph here. Because this is a probability distribution, the probabilities all have to sum up to 100%, which means this area here on the upper tail is going to be 100% minus 72, right? Because all of this error should be equal to 100%. So 100 minus 72, that gives us 28% on this upper tail. Now, because the normal curve is symmetric about the mean, that means if these Z-scores are the same, except this is positive and this is negative, and we're talking about area above and this is area below, these two areas will be the same. Again, because they're mirror images of each other. So if this is 28% of our curve's area, that means this part here below 0.59 is 28%. Which means this middle part now is going to be 100 minus the 2 times the 28%, because right, total area under the curve has to be 100, which means this middle part is going to be 44%. So again, if H naught is true, that means we have a 44% chance of a sample that we take will have a Z-score in between negative 0.59 and 0.59. So in other words, there's a 44% chance that a sample will have a population proportion in this area here. And one thing I have to warn you, when I looked this table up, I estimated it as 28, but your book estimated it as 27. So your book will say there's a 46% chance that your Z-score is here. So if H naught is true, then P naught is equal to 50%. There's a 46% chance that P hat, your sample, will give you something between Z equals plus or minus 0.59. So there's a 54% chance that P hat is not between Z equals plus or minus 59. In other words, it's outside in these areas, the yellow and the green area. So the p-value is greater than 50%, or 0.5, because the p-value here is 54%. So we do not reject H naught, because a sample does not support borrower's care one way or the other. So again, in other words, if we assume that the proportion is equal to 0.5, our sample, there's a pretty good chance we're going to get a sample with proportion equal to 0.51. So 0.51, our sample does not support rejecting H0. And remember, we'd never really come around to actually accepting H0. We simply reject H0. Our next problem, same data, 826 payday loan borrowers, 51% support regulation. We want to construct a 95% confidence interval of P, the proportion of payday borrowers who support increased regulation for payday lenders, using a sample proportion of 0.07. So that is, our P hat is going to be 0.7. So the first thing we're going to do is, for a 95% confidence interval, we need to know what z-score is associated with 95% of the data in between. So in other words, we're looking for the z-score so that between negative z and z, we get a 95% confidence interval. So an interval that's centered around our p hat over here, or our p, and we want to capture 95% of our sample distribution. Now our table looks like this. It doesn't show us in between two z-scores. It shows us a positive z-score and less. But if we draw this other, so this is our positive z-score, this is our negative z-score. If we want 95% in between our two z-scores, that means 100 minus 95, we have 5% left to divide between the two tails. And of course, because of symmetry, that means each of our two tails is equal to 5 over 2, which is 2.5%. So I'm going to make that note here. So each tail has the 100 minus the 95, right? So the 100 minus 95 divided by 2, 2.5 of the area. So each tail then has 2.5% of the area under the entire histogram curve. And this drawing still doesn't quite look like this, but it's not far, because essentially we can add this 95 and this 2.5, and we get this picture here for positive z and less. So positive z here and less is going to be 97.5%. And I'm going to make this note again. So on this table, I'm looking for 97.5% of the data. Looking at my table, I see I have 0.9750. So this is my 97.5%, and that's at z equals 1.96. So I'm going to note that down. And this is, your book uses the 95% confidence interval a lot, and it's always 1.96. And the other thing I knew to look around too, because there's that 68, 95, 99.7 rule that says that approximately 95% of the data is between two standard deviations, or z equals 2. But that's an approximation. A closer approximation is this 1.96. I can now calculate my standard error, square root, and again for hypothesis testing, we use our, we're not doing hypothesis testing, we're doing a confidence interval. So we're going to do p hat, and we were given p hat as 0.07. So our standard error is going to be our p times 1 minus p hat over n. So for p, we're using p hat, which is 0.7, 1 minus 0.7 over our sample size, which was given, over here, 826. So we get a standard error of 0.059, which means our 1.96, our z-score, times our standard error is equal to 3.1%. So our confidence interval is 70% plus or minus 3.1%, or we're looking at the interval 66.9% to 73.1%. And finally, we need to do our conclusion in terms of our actual sample. So we're 95% confident the true population proportion of those who support increased regulation is between 66.9% and 73.1%. At this point, we have reviewed how to determine when the sample proportion distribution is nearly normal, confidence intervals and hypothesis testing. Again, typically we don't know the population proportion, so for confidence intervals, we use p hat as our estimate, and for hypothesis testing, since we're assuming h naught is true, we use p naught as our estimate for p. We talked again about confidence interval, hypothesis testing, so our last topic is choosing a sample size. Choosing a sample size large enough that the margin of error, which is the part we add and subtract from the point estimate, the standard error, is sufficiently small for our purposes. For example, our task might be to find a sample size so that the sample proportion is within plus or minus 0.04 of the actual proportion in a 95% confidence interval. Our example, a university newspaper is conducting a survey to determine what fraction of students support a $200 per year increase in fees to pay for a new football stadium. How big of a sample is required to ensure the margin of error is smaller than 0.04 using a 95% confidence level? Looking at our formula for confidence interval, it's equal to our p hat, our guess, our proportion, our sample proportion, plus or minus z star times SE. The z star here, the z-score we have, it comes from our confidence level. The SE, that's the part that we're going to look at. Also, it does have n in the formula, the sample size, so this is where we're going to focus our attention. And again, our 95% confidence interval is what gives us our z, which is 1.96. And then our margin of error is square root of p times 1 minus p over n. This n here is what we're trying to determine. And we want this part here, this margin of error, to be less than 0.04. At this point, they haven't told us what p is, because at this point, they haven't gone out and done the sample yet. We're trying to determine how big the sample should be. So there's not any p hat for us to use. So what do we use for p is the question. So if we have an estimate, I don't know, from last year's or something, we can use it. Otherwise, the margin of error, this formula here, is maximum when p is equal to 0.5. So that is what we're going to use. We plug in 0.5 into our formula, so we have the equation 1.96 times 0.5 times 1 minus 0.5 over n square rooted is less than 0.04. We get rid of the square root by squaring the entire equation, so we get 1.96 squared times square root, we got rid of the square root by squaring everything, so 0.5 times, and 1 minus 0.5 is just 0.5 over n is less than 0.04 squared, and now solving for n, we get n is greater than 600.25. So we need 601 or more participants in our sample. And one last note, when one or more conditions are not met to use the normal curve, if the conditions for normal distribution are not met, the general ideas of confidence interval and hypothesis testing remain the same, but the strategy or technique used to generate the interval or p-value change, and these topics are for another course and another book. To review what we've covered in this video, 6.1, a lot of it is review of chapter 5, but well worth it. The first thing we did was identify when a sampling distribution is nearly normal, and that's based on two conditions being met. One, the sample's observations must be independent, and the simplest way that is met is if we have a simple random sample. If we have an experiment, that means people are randomly assigned to treatment and control. We have this success-failure condition, meaning we need at least 10 successes and 10 failures, or using the formula, n times p must be greater than or equal to 10, and n times 1 minus p also must be greater than or equal to 10. So when these conditions are met, the sampling distribution of p hat is nearly normal with mean equals p, and the standard error is equal to the square root of p times 1 minus p over n. A note, typically we don't know the true population proportion p, that's the whole point of why we're sampling, so we need to use an estimate. For confidence intervals, we use the sample proportion p hat to estimate p, and our formulas both for the success-failure condition and for standard error. For hypothesis testing, we assume h naught is true, so we use p naught for p, both in this success-failure condition and standard error. We did another example of confidence interval, an example of hypothesis testing, and last we talked about choosing a sample size so that we can satisfy conditions on our margin of error. And that's it for this video. Thank you for watching.